Hello, so today we're going to be going over the concept of refraction. So, in very basic terms, refraction is essentially the bending of light. Let's say you have two mediums, medium 1 and medium 2. Then let's draw a normal. As you can see, the normal is just the line perpendicular to the boundary between the two mediums, and you use the normal as a frame of reference for angles. Now, what angles in particular? Right now, there are two angles you need to know when it comes to refraction: the angle of incidence and, quite obviously, the angle of refraction. Now, let's draw a refracted ray. Okay, so as you can see, let's just make this a bit clear. Okay, as you can see, the ray is bending towards the normal, or in other words, it's refracting towards the normal. And this is our angle of incidence, and this is our angle of refraction. And as you can see, quite obviously, the angle of refraction is less than the angle of incidence, right? And now let's draw another scenario. Right, let's say you have another medium. You have another medium and another medium. This is our normal. Now we have a ray, but this time it's bending it's bending away from the normal. And as you can see, this is the angle of incidence, this is the angle of refraction, and this time the angle of refraction is greater than the angle of incidence, and it is refracting away from the normal. And always make sure that you're measuring the line, you're measuring the angle between the normal and the ray, right? You can't measure the angle like this angle. Don't do that, or don't measure this. You have to make sure you're measuring these angles. All right, now we've seen how refraction occurs. Let's see why refraction occurs. So I'll draw another diagram. 1 second. Okay, now once again you have two mediums. And now let's draw an example that we saw in the first scenario. This is a light ray and it's refracting towards the normal. Right? Now this whole time we've been assuming that the ray of light has negligible width, but in reality that isn't true. Right? So in reality, there's actually width in the ray. Okay, now this continues. Right, it's like okay. I'm not gonna draw it for all, but you see what I'm saying. So as you can see, this side enters the medium before this side, right? And another thing that I have to mention is that when a ray is refracting towards the normal, its speed is decreasing, right? Its speed, okay, towards the normal, speed decreases. Now, if its speed is decreasing, when it enters the second medium, this means that this part of the wavefront slows down before this part, and that essentially causes this causes the ray to refract towards normal, because one side, let's call this A and let's call this B. So since side A is slowing down before side B, right? And its portion and side B essentially continues at the speed of the ray in medium 1, while side A is at the speed of the ray in medium 2, that essentially causes it to refract towards the normal, right? You can imagine a scenario in which a car is entering mud, right? When it's entering the mud, one wheel hits the mud first, so it slows down first, while the other wheel continues at its initial speed. So that essentially causes the car to move towards an imaginary normal, right? So that's the case. And now in another scenario, let's consider this, right? Let's say you have a scenario in which it's refracting away from the normal, right? It's refracting away. So as you can see, similarly, you have side A and side B, right? And like I mentioned, if it's refracting towards the normal, your speed is going to decrease. But if it's refracting away from the normal, your speed is going to increase. So since side A hits the boundary first, it increases speed first, while the side B of the wavefront continues at its previous speed. So that is why it refracts away from the normal in this scenario. Right? Now another thing, I don't know if you've noticed, but as you can see in this scenario, right, it's refracting towards the normal. This is because side A of the wavefront decreases in speed before side B, and that's why it causes that's why it essentially refracts towards the normal, right? And another thing you can see is the distance between the wavefronts has decreased. So this is now the distance between the wavefronts, but before this was the distance between the wavefronts. And if you're not aware, the distance between the wavefronts is essentially equal to the wavelength, because the wavefront represents the same point on each wave. So that's why it's the distance between them is the wavelength. And now in this scenario, when it's refracting towards the normal, right, the speed is decreasing, and also as you can see, the wavelength is decreasing. So speed decreases, wavelength also decreases, right? And in this scenario, speed is increasing and wavelength is also increasing. Now you must be wondering why this is the case, right? This is because of the equation V is equal to F lambda, right? And a very important property you need to know is frequency. And frequency remains constant during refraction. Frequency is always constant. But as you can see, how will frequency remain constant if speed is increasing, right? Let's say in this scenario, when speed is increasing, when it enters the second medium, which has a higher, which light travels at a higher speed in, how will the frequency remain constant, right? Because the speed is increasing. That is why the wavelength also has to increase, because V over lambda is equal to F. So if velocity increases, then wavelength must also increase to keep the value of frequency constant. Similarly, in the first scenario where speed is decreasing, again you have the formula V over lambda is equal to F, right? And now in this scenario, light travels at a slower speed in medium 2. So now what's going to happen is speed is decreasing. So hence wavelength must also decrease in order to keep the value of frequency constant, right? Okay, so this is a very important equation that you need to know. And another thing is the concept of refractive index. So essentially, right, let me draw this. So again, you have, I'm labeling mediums randomly, so 1, 2 again, right? And then you have this ray that, let's say, refracts towards the normal like this. And then you have another, let's say, medium. This time it's also medium 1. But this time you have another medium, let's call it medium 3. And in this scenario, it's refracting more. It's refracting more in comparison because the angle of refraction here, right? The angle of refraction here is less than the angle of refraction there. So this means it's been refracted more, right? So why exactly, right? This is because of refractive index. Each medium has the property called refractive index, and refractive index is essentially a value given for how much the ray is refracted by, right? So this is refracted more, so this has a higher refractive index. Refractive index is essentially denoted by N. It's denoted by N, and in this case it's medium 3, so N3, right? In this case you have medium 2, so it's N2, right? So how do you calculate refractive index, right? So a lot of you must be wondering, how do you calculate this value? So the equation for calculating refractive index is essentially N1 times sine theta 1 is equal to N2 times sine theta 2. So in the first scenario, you have an angle of incidence and angle of refraction. So what the values you plug in, right? So let's say this is air. Usually they'll give you your first medium as air because air has a refractive index of 1, right? So you don't need to calculate the refractive index of air. It's usually given to you on your exams. It's 1, right? So now you just have sine theta 1 is equal to N2 sine theta 2. Now what you do is you measure the angle of incidence and the angle of refraction, and these are given to you. So your angle of incidence is in the first medium, right? It's theta 1. This is your theta 1. So you plug the angle of incidence in, calculate the sine of the angle of incidence, and then N2 sine theta 2. Sine theta 2 is your angle of refraction. This is theta 2. So you plug in theta 2, calculate the sine of theta 2, right? And then you divide your sine of angle of incidence over sine of angle of refraction to get your value for the medium. And that's how you calculate refractive index.